So we shall do a problem based on adiabatic process. 1 mole of a gas at 27 degrees Celsius expands adiabatically until its volume is doubled. Calculate the work done. Given gamma is equal to 1.4. So let's try to analyze the problem. So let's take out the values that we are needed. You know, it is adiabatic process and you have to calculate the work done. So let's recollect the equation for work done. W, that will be the first step that we'll be doing. W equals you had NR divided by gamma minus 1 times, as per our convention, TF minus TI. So this is the working equation we have to depend on. Now let us analyze the quantities based on that. We need N. N is the number of moles. So here it is given 1 mole. So I can say here given N equal to 1. So that is obtained. 1 mole of a gas. So it is not clearly specified whether the gas is ideal gas or not. But let's infer or let's consider this gas to be an ideal gas because no other data are given to indicate how to proceed in the problem. So in those cases we will assume these gases are ideal in nature. So at 27 degrees Celsius, so that is a temperature, you know. So temperature, I am writing T equal to 27 degrees Celsius, and you know what to do then and there. So you have to convert that into Kelvin. That will be adding 273, so it will be exactly 300 Kelvin. So I have converted into absolute scale. It expands initially until its volume is doubled. So volume is doubled means I can say VF, final volume will be 2 times initial volume. This is the data given there. So once again we have to look here. Its temperature initially was 27 degrees Celsius. What is the final temperature, that we do not know. So what is given here is the initial temperature Ti or T1. So we not given what is the final temperature, you know, as a result of the the adiabatic process. There will be a change in the pressure, volume as well as the temperature. So here what you are given is volume and temperature relations are given. Now you are also given gamma, the ratio of specific heat is equal to 1.4, that is given as data. Now just remember one thing, gamma equal to 1.4, it is the case of diatomic gas, diatomic. So in some problems you will be given gamma directly, or otherwise they can tell you that 1 mole of a diatomic gas. So when you say it is a diatomic gas, you will have to infer or you have to recall the value for diatomic gas, gamma is equal to 1.4. For monoatomic, the value for gamma, you know, it is 1.67. So depending on the problem wordings, you have to select the value of gamma properly. Okay. Now let us come back to our equation. So you are given NR is there, gamma obtained. You know that TI here, but TF is not given here. Instead of given TF, what is needed for us, what they have given is VI and VF. So it tells you that somehow you have to calculate the TF from the given values of VI and VF. So how do we do it? Let's see. You know, there are 3 forms of the equation of state for an adiabatic process. One of the equation of state is quite common and familiar to you, PV raised to gamma equal to a constant. Okay, a constant. So no mention regarding the pressure in the problem. So let us forget about this equation. It will not be of any use directly. So let us see what is the next equation. So since temperature and volume are to be related, I will have to depend upon the equation of state which connects temperature and volume. And hope you remember, if you memorize it correctly, TV raised to gamma minus 1 equal to a constant is another equation of state that will be of use to us. TV raised to gamma minus 1 is equal to a constant. See how to go from this equation of state to the second equation of state, it's a simple matter. I will just discuss how to go from this one to this one. If you do not memorize the second equation, if you need, what you can do is this one. See, PV raised to gamma equal to a constant already. So PV raised to gamma equal to a constant, say some constant C you can say, or C1. Now for ideal gas system, PV equal to nRT. PV equal to nRT. So what about PV by T? PV by T will be equal to nR, and n is a constant, R is a constant. So let me do this one. I am dividing this equation by PV by T. What is PV by T? It is equal to nR. So I am dividing on the right side by nR. So I think you understood what I am doing. I have divided the equation by PV by T. So on the right side I am dividing by nR, right? So C1 is a constant, nR is another constant. So the ratio of two constants will be some new constants. So let's say that is equal to some constant C. Okay, so what happens on the left side? P and P will get cancelled, and T will go to the numerator. So it will be T, and V is there in the denominator. There is a gamma on the top. So it will be, what will be the thing? T V. So since you reduce this V here, gamma minus 1. TV raised to gamma minus 1 is equal to a constant, and this is the relation that I have used here. Same manner you can get the third relationship, which connects pressure and temperature also, which is P raised to gamma minus 1 divided by T raised to gamma equal to constant. Just try it out yourself. So anyway, we need this equation here. It's quite simple. I need TF. So how do you write TF? I can write TF is equal to, TF is equal to, from this equation, Ti, or I can write TF by Ti. Okay, TF by Ti will be equal to Vi by Vf whole raised to gamma minus 1. That will be the equation. I am writing it final result only here. You can just do the other one. It will be equal to Ti into Vi by Vf whole raised to gamma minus 1. If you want, you can just calculate it here itself instead of substituting there. So what is Ti given? That is 300 into Vi by Vf. So what is Vi by Vf? Here it is. Vi by Vf will be equal to, I have to take 2 to the other side. So it will be 1 by 2. 1 by 2 is 0.5. So I can say it is 0.5. 0.5 all raised to gamma minus 1. What? Gamma is 1.4. So 1.4 minus 1. So it is 0.4. So just do this numerical calculation. You will get it around 227.36. Already it's worked out. 227.36 Kelvin, of course. So you got TF. So this is the way you got all the quantities. So nR equal to, now it's a mere just work of substitution. nR, n is 1, so 1 into R is, as usual 8.314 SI units divided by gamma minus 1. Gamma is 1.4 given here, minus 1, so that is 0.4 directly you can take, times TF. TF already we have calculated, that is 227.36 Kelvin, minus Ti is given to be equal to 300. So you can work out this one simply, and you will get this answer is equal to minus, there is a negative sign because here you can see TF is less than Ti, so there will be a minus sign thereafter, minus 1509.8 around this many. The units, do not forget to give the proper units, this many joules. So this is the adiabatic work done during the process of expansion. Now a word of just logical correction or logical checking. See, you obtained the work done in this problem as negative. You know why the work done should turn out to be negative, because it's given the process is expands adiabatically, and during adiabatic expansion the work is done by the system. Work is done by the system at the expense of its own internal energy. Hence, the work done as per our convention accepted, it should be negative. So let's add a comment as per our convention. Okay, W is negative as work is done by the system, I think I can just conclude it here, by the system, okay, at the expense of its internal energy. So hope you understood the problem. Let's wind it up. Thank you.